Imagine you and your best friend make a bet. You stay on Earth, he boards a spaceship and travels near the speed of light for what feels like a year to him. When he comes back, you've aged 10 years. He's barely changed. You lost the bet. But here's the thing. Nobody cheated. No sci-fi magic, just relativity. Time feels like a universal river. 1 second for you, 1 second for me, 1 second for an astronaut on the ISS. Einstein showed that's wrong. There isn't a single global now that everyone shares. The rate your clock ticks depends on two things, your speed and gravity. That effect is called time dilation, and there are two big versions. First version, speed time dilation, special relativity. The cleanest intuition is a light clock, two mirrors with a beam of light bouncing between them. Each round trip is one tick. Inside the spaceship, the light goes straight up and down. Tick, tick, tick. Normal. But to you watching the ship fly past, the light has to travel a longer diagonal path, because the ship moves sideways while the light bounces. And since the speed of light is the same for everyone, a longer path means each tick takes longer. Same speed, more distance, more time. So the moving clock runs slow compared to yours. And it's not just the clock. Every physical process on the ship is tied to time. Chemical reactions, atoms vibrating, your heartbeat, your brain. The traveler isn't feeling slow. He feels normal. It's only when you compare clocks that the difference appears. At everyday speeds, the effect is tiny, but near light speed, it becomes huge. At about 99% of light speed, time can run roughly 7 times slower for the traveler. Push closer, and the gap explodes. That's why people call fast travel one-way time travel to the future. You can experience less time while the outside world experiences more. And this isn't just theory. We see it with fast particles, like muons, created in the upper atmosphere. They should decay before reaching the ground, yet many survive because, in our frame, their internal clock is time dilated. Second version, gravity time dilation, general relativity. Gravity doesn't just pull on things, it warps space-time, and that changes how time flows. The deeper you are in a gravitational well, the slower your clock runs compared to a clock higher up. A useful connection is gravitational redshift. Light climbing out of gravity loses energy, shifting to redder wavelengths. The same space-time geometry that redshifts light also makes clocks tick at different rates. This is happening right now. A clock on the ground ticks slightly slower than a clock on a mountain. The difference is tiny but measurable with modern atomic clocks. GPS proves it every day. Satellites are higher up, weaker gravity, so their clocks tick faster than clocks on Earth. They're also moving fast, which slows their clocks a bit. When you combine both effects, the satellite clocks still drift relative to the ground by tens of microseconds per day. If engineers didn't correct for relativity, GPS errors would grow by kilometers in a single day. Time dilation isn't experimental. It's in the navigation on your phone. Speed and gravity can even fight each other. On the ISS, being higher up makes astronauts' clocks run a little faster, while their orbital speed makes them run a little slower. The net difference is small, but it's real, and it's measurable. So what about the famous twin paradox? If motion is relative, couldn't each twin say the other one was moving, so the other should age less? The key is that the traveler changes frames. To leave Earth, turn around and come back, you accelerate. The stay-at-home twin doesn't do that. In relativity, the time you experience is the length of your path through space-time. Different paths between the same two events can have different lengths, so one twin can genuinely experience fewer seconds. No contradiction, just geometry. Now take gravity to the extreme. Black holes. Near a black hole, time dilation can become dramatic. As a thought experiment, imagine hovering very close to the event horizon, while a friend watches from far away. To the distant observer, your clock appears to crawl. Your motions look stretched out. To you, your watch ticks normally. Hovering that close would require absurd thrust, but the time dilation point stands. This idea inspired Interstellar's 1 hour equals years scene. The movie simplifies and dramatizes things, but the core physics is real. Strong gravity can make two people experience wildly different amounts of time. So what does this all mean for you? Right now, sitting where you are, time is passing slightly faster for your head than for your feet. Because your head is a tiny bit farther from Earth's center, a tiny bit less gravity, time flows microscopically faster there. It's an undetectable difference in everyday life, but the difference exists. You are living inside a universe where time is flexible, where speed and gravity literally reshape how fast you move through time, where two people can experience completely different amounts of time during the same event, and both be completely correct. Einstein didn't just change physics, he changed what time even means. And the next time you look at your phone for directions, just remember, engineers had to bend the rules of time itself just to tell you where to turn. That's time dilation. If this broke your brain a little, good. That means it worked. If you enjoyed this, like and subscribe for more fast space explainers.